Hi everyone, thanks for inviting me to open this conference tonight. Today we'll talk about the temporal variability of groundwater recharge and the implications for site management. This is really the result of the work that I've been doing at the Morwick G360 Groundwater Research Institute at the University of Guelph in Canada, working with some amazing colleagues and professors like Professor John Cherry and Professor Beth Parker, who is the director of the institute, that are the co-authors of this talk. And before I move forward, I want to acknowledge some of the co-authors of the papers that I will cite throughout the talk: Ken Walton and Steve Murray and Darren Abbey with Matrix, some of the sponsors, the Boeing Company, NSERC Canada, and the University Consortium, and all the amazing colleagues and friends who participated in field work from the Morwick G360 Institute and from Stantec. When we talk about groundwater, we should remember that groundwater represents 99% of the liquid fresh water on Earth. So what we see, the 1% is just really the tip of the iceberg, which is the surface water, meaning lakes, streams, wetlands, but the majority of the water on Earth is groundwater. And groundwater is used globally for drinking water purposes. It's been estimated that at least 50% of the global population drinks groundwater, and approximately 2.5 billion people depend solely on groundwater resources to satisfy their basic daily water needs. Moreover, groundwater is also the primary contributor to stream flow. Aquifers supply on average 50% of river base flow, but they have also important eco-hydrological function because aquifers provide stable temperature habitats, supply nutrients and inorganic ions, provide moisture for riparian and other groundwater dependent vegetation. And globally, water coming from wells contribute to 43% of the total water used for irrigation. Of course, there is a large variability across the world. And here I've highlighted the Brazil number that on average is 19%, but there are some local areas where this percentage is more than 80%. However, when considering that groundwater provides 50% of the base flow to the rivers, it is fair to say that then it also provides an additional 30% of the water that is used for irrigation. So globally, as was pointed out by Wood and Cherry in this editorial on groundwater a few years ago, groundwater use for global irrigation is 70% of the total. But despite its importance, in the past decades, groundwater has been misused. Mismanagement of groundwater in the past few decades caused groundwater depletion and groundwater contamination. And we see the effect these days of this mismanagement with land subsidence, reservoirs that have been drying because of droughts, health issues, overpumping for irrigation and for farming, seawater intrusion, and also salty soil. And these challenges are exacerbated by climate change and will be even more in the future. Climate change projections indicate that many mid-latitude and arid and semi-arid regions will likely experience less precipitation, and there will be a likely shift to more intense individual storms and fewer weak storms. And when we look at a map of these drylands areas, they cover 41% of Earth's land. And they have an important function because 30% of world's population live in this area. There is 50% of livestock in desert and drylands. And there is, most importantly, 44% of all the cultivated land is in these areas that will likely experience less precipitation. And in these regions, groundwater is key because it provides the resilience to droughts. Because during droughts, surface water reservoirs disappear and groundwater becomes the only source of fresh water. And here we see an example from California, from a recent drought, of Lake Oroville completely full and then empty during the drought. And with droughts becoming more frequent, groundwater will become even more important. So we need to understand what is the impacts of these meteorological droughts on groundwater, because as said, drought has a faster effect on surface water and soil moisture. The decline in water level, though, is delayed because of the slow passage of recharge pools through the thick veda zone. So we need to understand what is the magnitude of the impacts at the water table and what is the time lag that there is between the climatic input and the groundwater. And one way to look at this is to explore droughts from the past, because major drought conditions that we are experiencing now are not outside the range of natural variability. And this is here an example from a study who compared the precipitation during the recent California drought to tree-ring reconstruction, finding that precipitation during the drought has been low but not outside the range of natural variability. So we can look at the effect of paleoclimate on groundwater because it can provide important insights. However, these paleoclimatic studies don't focus on groundwater. Commonly, the information deduced from these studies pertain to air temperature, precipitation, vegetation, surface water, but not groundwater. However, climate modifications influence greatly groundwater recharge, and in particular, when we will see the effect of these climate modifications, we need to look at two important processes: the net infiltration, which is the water draining beneath the ET zone in the unsaturated zone, sometimes referred to as drainage or percolation, and the recharge, which is the water that enters the groundwater flow system, so contributing to the replenishment of the groundwater reservoir. These two processes are usually considered the same when the unsaturated zone is thin, but when the unsaturated zone is thick, the two rates are different and they need to be treated differently. But why is important? It's important because for contaminated site. It's important because the net infiltration represents the flux of water that moves the contaminant from the surface to the water table, and the recharge, representing the upper boundary of the three-dimensional groundwater system, governs the flux of groundwater available to transport contaminants in plumes. So these are really two key processes that needs to be understood. And information on the multi-decadal variability of groundwater recharge rates can be archived in the unsaturated zone. There was a review paper that came out a few years ago about using these unsaturated zone hydrostratigraphies, but almost all the studies were conducted in porous media. But so what we tried was to use a similar approach, but adapted for a fractured porous rock site, and using pore water chloride concentration profiles to reconstruct groundwater recharge variability over 5 centuries. And the study area is in Southern California. It's a semi-arid upland area where the average precipitation is 450 millimeters, and the potential evapotranspiration is 3 times the average precipitation. The bedrock is the Chatsworth Formation. It's a late Cretaceous turbidite marine sequence. It's densely fractured with bedding parallel fractures as well as vertical or near vertical joints and faults. And as you can see, the matrix porosity is in the order of 2 to 20%, whereas the fracture porosity is 10 to the minus 3, 10 to the minus 5. And I'll now describe what is the logic of using pore water chloride from veda zone to reconstruct recharge history. So we have constant chloride deposition from the atmosphere via dry fallout and precipitation. Then water with chlorides infiltrates into the ground and is subject to evapotranspiration. The evapotranspiration takes up the water but not the chloride. As a consequence, chloride concentration is greater by a factor that is proportional to the evapotranspiration. Then water crosses the bottom of the root zone, having a certain chloride concentration, which is really the effects of the climate conditions, so of the evapotranspiration. And therefore, high chloride concentrations indicates high evapotranspiration and therefore low net infiltration. And vice versa, low chloride concentration indicates low evapotranspiration and therefore high net infiltration. This water that crosses the root zone pushes down the old water. And this is assuming a piston flow type movement. And therefore, the vertical variability of chloride concentration in the unsaturated zone can be used to understand the effects of past climate conditions. And this is a rather complicated slide, but it's just to, again, show our approach. So here on the left, we have a vertical profile of chloride from field data of chloride concentration with depth. At each depth, we calculate the cumulative mass of chloride, and assuming a constant input from the atmosphere, this chloride mass corresponds to a certain pore water chloride age. At the same depth, the concentration will give an indication of wetter or drier conditions, as we explained. Combining these two information, so concentration and the cumulative mass, so the age, we can reconstruct a recharge index as deviation from the average recharge conditions. So when is 1 is double the recharge, when is -1 is half the average recharge conditions. And looking at this index for the past 500 years, what we found was that the extreme values of this index are -90% and +80%. So this is the range of variability in recharge at the site, but that the majority of the values are between -50% or +40%. So this is really the expected variability. That over 5 centuries there is a linear decreasing trend, showing then that recharge is decreasing over this period. But most importantly, there are these oscillation around the average, so around the zero, of climate oscillations and therefore recharge oscillations between wet and drier periods, with the wet being the blue and the dry being the yellow. And when we compared this recharge index reconstructed with chloride concentration in pore water with 3-ring reconstructions, what we found is that the change in phases, so between wet and drier conditions, were consistent between the recharge index and the 3-ring reconstruction. And therefore, there is clearly a control of past climate conditions on recharge and also on the distribution of chloride in the unsaturated zone. And most importantly, there is also a similar linear trend during the same analyzed period. So what is the take home from these initial results? That really these chloride profiles can show most directly the variability of groundwater component of the hydrological cycle, that at our study site, over 5 centuries, the net infiltration varied between -50 and +40% of the average value, and there is this cyclical trend of recharge that appears to be connected to this atmospheric forcing pattern. And it is fundamental to detect this natural variability of recharge, because we need to identify this to analyze all the diverging trends caused by human-induced climate change. However, we are interested in understanding what happens at the water tables where the unsaturated zone is thick, like in our case study. And so to do that, we used an integrated surface water groundwater numerical model, MikeShe. MikeShe is a commercially available software developed in Europe and used globally. And so what we did, we investigated the period 1992 to 2017. In this period, the average precipitation is 415 millimeters, but we have periods of wetter than average conditions, like a wet period from 1992 to 1998, where the precipitation was 63% higher than average, and the dry period, so from 2011 to 2016, where the precipitation was 42% lower than average. Then the question we asked was, how does recharge change during wetter and drier periods? And so we ran the model, we parameterized the model, we calibrated the model, then we ran the model, and we came up with the average annual recharge map that will give us an indication of also of the spatial distribution of recharge in a catchment of our study site. And what we found is that for the 25 years of simulation on average, you will see that the average value is very low, and also we have focused recharge conditions. That means the majority of the area shows very low, if or even null recharge. But then there are some areas with where recharge is very high. But then when we did consider only the wet period, so from 1992 to 1998, what we see is that the average recharge is 22 millimeters, so it's about 60% higher than the average, the long-term average, and also that the spatial pattern is even more focused. So there are even more areas with low recharge, but the few cells that simulate high recharge, the values of recharge are even higher. But most importantly, when we looked at the drought period, we found a completely different pattern and kind of surprisingly also a similar average recharge. So really recharge didn't change during droughts, was only 10% less than the average. However, was a lot more distributed. But why is that? To investigate the reasons for this behavior, we extracted the time series of infiltration, so the flux at the surface, the net infiltration, so the flux beneath the root zone, and then the recharge, so the flux at the water table for the wet and the dry period. And as we see, the simulated infiltration is of course higher during the wet period, and in this period from 1992 to 1998, we have also some important episodes of flow at the bottom of the root zone. So there is a replenishment of the deep unsaturated zone, and deeper at the water table we have also we have an important recharge trend here. As we can see, there is almost like a constant recharge, but also with a few episodes of high recharge in correspondence of the high precipitation event. But what is interesting is that observing the dry period, of course, as we say, the infiltration is lower, and in fact, as a result, the net infiltration is almost null. And this is because all of this infiltration water is used by the evapotranspiration. However, when we look deeper into our profile at the water table, we see that there is a constant flux at the water table. So recharge is always occurring, even during the driest period, with this water coming from the unsaturated zone that almost acts as a storage for the groundwater. So concluding, what we found is that the simulated recharge flux is nearly steady over the simulated period, suggesting that the variability in precipitation and in net infiltration minimally impact recharge fluxes across the water table. And this is likely because of the low values of recharge, that is, as I said, only 3% of precipitation, and the dampening effect of the thick unsaturated zone. So really where we have this thick unsaturated zone, there is less recharge variability expected, but where the unsaturated zone is thin, we expect the variability to be much. And this leads us to a pending paradigm shift in natural resource damage. Natural resource damage is the language that has been used in the US for groundwater contamination, and really that has been the impetus for pump and treat. But yet, pump and treat is converting a water quality impact into a water quantity impact when we think of the disruption of the flow system and so on. And this will become increasingly important as more severe droughts come with water scarcity. Globally, groundwater extraction has increased more than 4 times in the last 50 years. As we see around the globe, there is a continual decline of groundwater levels, indicating that groundwater is being pumped in excess of recharge. And this is the case for all the continents everywhere across the world. But what many people don't realize is that this groundwater depletion contributes substantially to sea level rise. It was in fact estimated by Wood and Hinban in 2018 that groundwater depletion can contribute to 25% of the current annual sea level rise. That is the same percentage, the same contribution coming from melting glaciers and ice caps. So that is more as a larger impact than what we normally think. So concluding, there is too much fresh water, which is either natural runoff or pumped groundwater that is escaping to the ocean. We must focus on reducing these volumes wherever we can, promoting engineered recharge. And this needs to be factored in when planning remediation strategies. This was my last slide. I want to thank you for your attention and for the opportunity of presenting. I'm leaving you with some pictures of the amazing research we conduct at the Morwick G360 Groundwater Research Institute. Please check out our website. We have some amazing researchers and students and staff, and I think it will be very interesting for the audience of this conference. Thanks, and I'm here if you have any questions.